Hey guys, I'm here with OpenQuant, ready to solve question number 1, repeated rolling. Now this question poses a hypothetical where we repeatedly roll a fair 6-sided die until we first encounter a number which we have already seen. R is then denoted as the number of times a die was rolled in this particular game, and P sub R the corresponding probability. Let's walk through a hypothetical. Say on the first roll, you get a 3, the second roll a 6, the third roll a 2, and on the fourth roll you get another 2. So the R value for this game would then be 4. And P sub R would then denote the probability of such a game occurring where there are exactly 4 rolls. Let's now jump into the first sub-question of this problem. So this question asks us to calculate P sub 3, or the probability of a game taking exactly 3 rolls. In order for a game to take exactly 3 rolls, 2 conditions must be met. The first is that the first and the second roll must differ. Otherwise, the game would terminate early before we got to the third roll. The second condition is that the third roll must be either the value of the first or the value of the second roll, thus terminating the game with 3 rolls. We'll start by counting all the valid ways that we get exactly 3 rolls. So the first roll could take on any of the 6 values. The second roll can take on any of the values except whatever the first roll was, thus yielding 5 possible values. And the third and final roll can only take on 2 values, and they are the first or the second value, 2. We are then asked to solve the probability of exactly 3 rolls. And for each of these individual rolls, there are 6 possible outcomes because a die has 6 different faces. And since each of these rolls are independent successive events, we can then multiply across to get our P sub 3. So this would get 10 over 36. 5 over 18 equals P sub 3. The second sub-question asks us to compute the value of P sub 1 plus P sub 2 up to P sub 10. When approaching a problem like this, I find it's helpful to consider the edge cases. So let's think about P sub 1 and what that holistically means. P sub 1 is the probability of rolling exactly 1 time. But if we remember, this game required us to roll until we see a duplicate value, and it's impossible to have seen a value that we have already rolled on the first roll. As a result, P sub 1 is equal to 0. So now look at the other end of the sum, P sub 10. In order to get an event where there are 10 rolls, we would have to have seen different values and on the 10th roll seen a duplicate. But because a die only has 6 sides, we are guaranteed to see a repeated value by the 7th roll. Therefore, not only P sub 10, but P sub 8, P sub 9, and P sub 10 all equal to 0. And the sum reduces down to P sub 2 plus P sub 7. However, upon inspection, we can see that the events corresponding to these probabilities span the entire outcome space, meaning that one of them is guaranteed to happen, and as a result, the sum is equal to 1. Alright, so the third and final sub-problem to this question asks us to compute P sub 5 given that this iteration of the game has taken at least 3 rolls. Now guys, when you see the word given, I would really like for your mind to jump to Bayes' rule, given that it is the formula and theorem for conditional probability. Bayes' rule states that the probability of A given B, that's what this vertical line denotes, is equal to the probability of A and B divided by the probability of B. And in this case, A is the event P5, so exactly 5 rolls, and B is the event at least 3 rolls. And we're asked to solve the probability of A given B. So now we can compute the numerator and denominator of this expression independently and use Bayes' rule to compute the conditional probability. So the probability of A and B is, well, let's just think about what that means. It's the probability of taking exactly 5 rolls and at least 3 rolls. And intuitively, we know that if it takes exactly 5 rolls, it's going to take at least 3 rolls. So that second expression, this B expression, is a little bit redundant and actually reduces down to the probability of just taking exactly 3 rolls. Because if it takes exactly 5, it's taking at least 3. We can compute the probability of taking exactly 5 rolls by a similar approach that we did in the first subproblem. So there are 5 rolls, and the first one can take on 6 values, the second 5, 4, 3, and then on the 5th value, which terminates the game, it must equal one of the previous 4 distinct values, so 4. And we divide each by 6 possible outcomes of the die, multiply through, because they're independent successive events, and we get, let me make sure I don't do my math wrong, 5 times 4 is 20, times 3 is 60, times 4 is 240, divided by 6 to the 4th. You can simplify this to 40 over 6 cubed. And this is probability of A. Now let's solve probability of B, which, just to reiterate, is probability of taking at least 3 rolls. This is also equal to P sub 3 plus P sub 4 all the way up to P sub 7, just because P sub 3 is the probability of taking 3 rolls, and so on and so forth up to 7. And at least 3 rolls implies that we are looking for the probability of it taking 3 or 4 or 5 all the way up to 7 rolls. And we know how to solve each of these individually, but rather than do that tedious method, I propose that we use the complement rule, simply because the entire outcome space is clearly divided into P sub 2 taking exactly 2 rolls, and P sub 3, P sub 4, all the way up to P sub 7. And the total sum of these events is 1. As a result, this expression that we're looking to compute is equal to 1 minus, right here, P sub 2. And P sub 2 we can calculate very easily. Simply, the first one can take 6 over 6 possible values, and the second roll must take the value of the first, 1/6, which is, as a result, this expression is 6 over 36, or 1/6. And this expression, plugging it back up into here, is equal to 5/6. And then this right here is probability of B. So now we'll use Bayes' rule. We're going to go all the way back up to the top and use this expression right here. Probability of A given B is equal to the probability of A and B, for probability of B. And this reduces down to probability of A, which we kind of rationalized up here in this expression. Divided probability of B is equal to, let's see, 40 over 6 cubed. And instead of dividing by this, I'm just going to multiply by the reciprocal times 6 over 5. This is probability of B right there. This is 8 over 6 squared over 8 over 36, which I know to be approximately equal to 0.22, and I just verified that with a calculator. We're now going to do something that I just find particularly interesting and helpful in understanding the intuition behind these problems, and that's simulating our results via code. I simply use the random package to generate random dice rolls, and that's what this roll function does. I then use that to simulate an actual iteration of our game where it returns the R value for that particular game. I then have 10,000 runs of the game, and I only add the results of that game if the value is at least 3. And of these values of at least 3, I then count the number of 5s and get the corresponding proportion. This corresponds exactly to what we're solving for in the third subproblem, which is P sub 3 given at least 3 rolls. We'll now run this experiment to see what the real life proportion comes out to be. As you can see, it's 0.217 in the first run, 0.225 in the second. So as you can see, our results are converging very closely to 0.22 repeated, which is what we derived the theoretical value to be.